County, people are.
Huge.
Never any of this thing. What happened here?
Okay, let's see, do we have any more white chalk around? Sort of. Well, we have a little bit left. All right. I'll bring another box. Okay, so let me back up and just review a little bit so that we get back into the swing of things. All right, so last time I was talking about GRT modules and GRB modules. And so the way to think about this is we already know what sort of GR modules look like. GRT modules are just sort of things in the graded category. So the way to think about this, these are graded GR modules. Okay. And so let me kind of recall some of the notation. Are nice after this. So let's see. Well, we had these modules. We had these C's, and this was induction from B to GRB lambda. Okay. And we had ZR without the prime, and this was co-induction. And this would be plus, GRB plus. Okay, so these are sort of lifts of the baby Burma modules that I defined earlier. And the nice thing is we can use these modules for classification. So the simple, let's say GRT modules, they're in one-to-one correspondence with his weights. So I'm going to take a weight lambda over here. What I can do is I can sort of express this weight, let's say as lambda 0 plus p to the r lambda 1, where lambda 0 is in XRT. And then I can sort of express my irreducible L lambda. I guess I put a hat in R over here. And this is L R hat lambda 0. And then since this is a multiple of p to the r, you just pull it outside. So this is p to the r. Okay, and this so this weight is in XRT, and so this is actually a GR. This is a simple GR model. We know that simple GR modules are G modules. So therefore it's a GRT module. You just go up to G and then you restrict it down to GRT, and then so this makes sense. Okay, any questions on this? All right, so now I can get back into looking at the structures of these higher homologies. So let's restate the proposition again, which we'll prove. So for each weight and I and N, there exists an isomorphism of G modules. Okay, and So if I take HI of lambda, okay, this I is the same as the one over here. This is going to be RI induction. So I'm going to go from GRB up to G. And then I take the CR prime half. So this induced module. Okay, so we can express these higher cohomologies in terms of induction from GRB to G, like this particular module here. All right, so let me give you a proof. Proof is actually not too hard, I believe. If you are familiar or comfortable with spectral sequences. Right. So what we can do is we can compose the two induction functors. So there exists a spectral sequence, and looks like the following. So again, this is one of those Grothendieck type spectral sequences where I'm sort of taking induction and another induction and composing the two. So so basically you do the following. You have Rm induction from B to G. We just write it this way. Sorry, this is GR. Okay, and then you take Rn induction from B to G of lambda. This should be a GR. All right, so I'm taking the functor induction from B to GRB, and I'm composing it with induction from GRB up to G. And now, you know, induction is transitive, so the composition of the functors is just induction from B to G. So this will converge to the higher right derived functors of the composition. So that looks pretty good. And now you just make the following observation. So if I take Rm induction from B to GRB of lambda. Well, what does induction of B to GRB look like? Induction of B to GRB. Well, when I take the quotient, it's affine. So this functor is exact. We sort of saw this before. You know, if you take the other functor here, let me just write over here. So let me just kind of give you a general idea. So if I take like sort of the other functor in terms of co-induction, and I'm taking something like this, lambda here. Okay. And so this functor is just sort of tensoring as a vector space. It's just tensoring, and then you get this to UR plus or something. Okay. So essentially, you know, when you're doing this functor as vector spaces, it's just tensoring over K. So that this functor is exact. All right, and then this is sort of dual to this, so this functor is exact too. So if I have an exact functor, what do I know about the higher cohomologies? Anyone? Here. Okay, so this is 0 for n bigger than 0. Okay, so that means that this spectral sequence only lives on one line, right? And it'll collapse. So the spectral sequence collapses. Okay. And therefore yields that RM induction from GRB to G of R0, I'll be very explicit, B of GRB of lambda isomorphic to RM induction from B to G of lambda. Okay. Now, this is just induction, right? So I think we're done. So this you could just write it this way, and this is this module right there. Remember, this is just C R prime and lambda. Okay. All right. Any questions on this?
So what was it before? Or is that what you meant?
Sorry, I didn't quite understand the question.
Before you had the parentheses in? You see it composing?
Well, it was just R0.
Oh, I see, I see.
Yeah, I mean, I just took the, yeah, so I just took R0. Okay, so this finishes it. All right, great. Okay, so let me remind you of Kemp's vanishing theorem. Okay, so what does Kemp's vanishing theorem say? So let lambda be a dominant rate. So then, if I take the higher cohomologies, this is 0 for I strictly bigger than 0. Okay. All right, now, yeah, so now what I want to do is, I want to look at the H zeros. Actually, before I do that, I want to define something a little bit more generally. Okay. All right. So this definition is due to Steve Donkin. So let M be a G mod. Now, this is actually a new definition. I want to define the notion of P-filtration. So M has PVR filtration. If and only if there exists a sequence of P modules. So let's see, how am I going to label this? I want to label it so it's at least consistent with what I have.
Can I ask you a quick question?
Yeah.
For Kemp's vanishing, is that any lambda or is that predominant?
Oh, sorry, this is Don. Sorry. Okay, thanks for pointing that out. Okay, so I want to define the notion of P filtration. Sometimes this is called a good P filtration. All right, so what I need is a sequence here. So let's say it's M0. This could be the 0 module. M1, M2, all the way up to MS, which is actually equal to M, such that when I take the successive quotients, this is of the form L lambda 0 tensor of H0 lambda 1 twisted R times, where lambda 0 is some restricted weight and lambda 1 is a dominant. So these sections are not just H0s. They're the form irreducible tensor H0 twisted R times. Okay. Now, I haven't given you much motivation for this, but later on, what I'm going to do is I'm going to show you how this is related to what's called Donkin's tilting module conjecture. So I kind of want to introduce it now because the next result that I'm going to go over involves showing that H0 lambda has a P filtration. All right. Any questions on this? All right. All right, so there's a question that Janssen actually gave back around 1980. So Janssen. He asked the following. So let lambda be a dominant weight. So the question he asked is, does H0 lambda have a good PR filtration? Okay. So I think you know what everything means. I mean, this is just an H0 like we normally know, and it has, Boyle's character formula, the character formula for this thing. And so the question is, does it have a filtration where the sections look something like this? All right, so this problem was sort of open for a while. And in 2013, so this is around 1980. So this is around 1980. So in 2013, Marshall and Scott proved the following. So if E is bigger than or equal to 2H minus 1, this sort of bound that I have for the listed character formula. So if this is true, and the listed character formula holds. So suppose that the listed conjecture holds for G. Okay. So then the H0 lambdas all have good filtration. Good. We don't have a good filtration. Have a good PR filtration. So as long as the prime is big enough and Listic's character formula holds, they actually prove this result. And last year, we actually proved that this is not true. And we have lots of counterexamples now for this. So let's say 2019. So Chris Bandel, myself, Cornelius Killen, also logic showed this question is not true in general. So we found counterexamples. I'll just say counterexamples because we have lots of them. To nonsense questions.
The question here, do you have, can you like P vary? This is still a characteristic of the field.
Yes, yeah, P is a characteristic of the field. Yeah.
So do you find things that work for no P?
What?
Did you find counterexamples that work for no value of P?
Well, we found a counterexample for P equals 2 in G2, for example,
Oh, I see.
which is less than the Cox 2H minus 1. So I'll just put an example. So for example, G being equal to G2. Let me just say phi equals G2. It's kind of confusing if I put G2 down. You may think it's a Frobenius kernel. Okay, so and the root system is G2 and P equals 2. There's counterexamples. And we also have counterexamples for type Bn now for P equals. Okay, any questions on this so far?
And so could it still happen in this case that it has a PR filtration for this different P?
Sorry, can it?
And have a PR filtration for different P. So like, I guess this is saying there doesn't exist one of those filtrations for P equals 2.
Yeah, so for a certain weight and P equals 2, for certain H0, it doesn't have pure filtration. Okay, I mean, this result says that as long as this is true, and this is true, then this thing always has a good pure filtration for any weight. This is for all
Oh, I see.
dominant weights.
It's more a question about finding small characteristic fields.
Well, yeah, I mean, the thing is, we're not quite sure. Okay. It turns out that this is related. There's a more general conjecture about when a module admits a good P filtration involving tensoring with the Steinberg module. So I haven't introduced that yet. Okay, so what I'm going to do is I'm going to start building towards this now. So, I mean, all the questions you asked are good. I mean, and there's a lot of new research that we've done, which connects this good PR filtration with Donkin's tilting module conjecture and sort of other ideas. So I have to introduce Donkin's tilting module conjecture also.
So these counterexamples, are the weights relatively small or big for which you have these
It's not too small. I mean, it turns out once they're big, then you could actually show that this is actually true. And this is a really good question. So what I'll do next is I'll actually show you how to construct these PR filtrations for H0. And the way we're going to do it is we're going to use this trick involving this factoring the H0 in terms of induction from GRB to G. And so that's why I wanted to introduce this notion first. And we'll use what we've done and apply this. Okay, other questions? All right, good. All right, so now I'm going to give you a theorem which actually allows you to construct these PR filtrations. All right, so here we go. So let me up this to a theorem. Okay, here we go. So let lambda be in xt plus. Okay, so it's a dominant weight, and let's assume every composition factor of the induced this is baby Roman model, ZR hat prime of lambda, okay, has the form LR hat mu 0 plus P to the R mu 1. And here, of course, this is an XR and V1. Okay, so now remember, in terms of GRB composition factors are basically the same as GRT. So tensor plot. And this mu1 can actually just be any weight you want. Okay, so if you take a composition factor, it's going to look like this. Okay, it's going to be able to factor in terms of a restricted simple module tensor, some one-dimensional representation. Okay. Now, I haven't really said anything. I have to actually say what the conditions on mu are. So such that, well, I just want it to be pretty dominant. So I want to take mu1 plus rho, inner product to be bigger than or equal to 0 for all simple roots. Right, so you kind of want it to be like a little bit more than dominant. You want when you add rho to it, you add beta check, then you want it to be bigger than or equal to 0. Actually, what I'm saying, the mu1, let me say this one. This automatically is make sure that mu is actually dominant. So you could also include the weights sort of close to that wall, you know, involving like the BBW. Okay, so the conclusion is that H0 lambda has good PR filtration. It has a filtration of this form over here. And moreover, if I want to know, if I know the composition factors of this, let me say it this way. So the number of times this composition factor occurs, the GRB module is the same as going to be the number of times zero tensor H0B1 twisted appears in this filtration. So once you show this has a good PR filtration, with that particular good PR filtration, you want to know the number of times this one actually occurs as a subquotient in this filtration over here. And it's actually equal to the number of times this occurs in the composition factor. And I should probably put a hat in it too. Okay. I don't know, maybe. Okay, so I guess these are G modules. Remember. Okay. Any questions on this? Okay. All right, so what we'll do is we'll use the setup that I had before. Prove this. Okay. All right. So here's a proof. Okay. So let, okay, so suppose we have a composition factor. So let LR hat mu0 plus PVR mu1 be a comp factor. Let's see, CR hat. Okay. Now let's just apply R1 to this, see what happens. So it turns out that when you write R1, GRB of G, of this composition factor, LR 0 tensor PVR mu1. So this is a restricted weight over here, this mu0. And so it's a G module. So I can use the tensor identity to pull it outside. Okay. So this turns out to be LR mu0 tensor R I induction from GRB to G of P to the R mu1. Okay. Now, what you can do is there's actually a theorem which says that you can identify this with HI of mu1 twisted. So I'm not going to prove this theorem, but we want you to look in the book. This is HI mu1 twisted R times. Okay, so this is by some the theorem which actually proves it. Okay. So the upshot of it is that whenever I apply RI induction from GRB on this thing, then I get a section which looks like the stuff you want for a good P filtration. Oh, sorry. This should be an R's. Okay, this is okay. This is true in general for RI. So in particular, if I is equal to 0, then we could do something, right? So what we do now, let's set I equals 0. So that means that induction from GRB to G of this thing, and the 0, that's a PRmu1. And I'm just going to go down to the bottom line. So this is LR mu0 tensor H0 percent. Okay, so this does look like a good P filtration factor. All right, so what's the idea? Well, the idea is to use that isomorphism that we had before involving, let me just do this. So recall, let me just write this out. So if I want to factor H0, induction from GRB to G of ZR hat prime lambda. Okay. So the idea is I'm going to take a composition series for this, all right, and then I'm going to hit it with the induction factor. Okay. So take a composition series for ZR. Okay, so let's do that. So I have 0 is equal to, let's see, it's M0, M1. Let me use, instead of M, let me use N because it's a little confusing. Well, I erased it off the board, but I use the M's before for something else. So let me just use N here. Okay, so then I have N sub S, which is equal to ZR prime lambda. Okay. Now, this is a composition series for this. So when I take Ni over Ni minus one. That's like L, I mean, it's of the form L mu zero plus something else. For some mu zero and mu one. Okay. All right, so we have this. Now, I'm going to apply induction to everything. Induction is left exact. Okay, so everything is good. So apply induction. Yeah, apply, let me be more specific. Apply the induction from GRB to G of one. Okay, so I apply this to everything in sight. This is contained inside of induction GRB. So, okay, all the way up to induction on this thing, which we know is H0. All right, so now everything looks pretty good in some sense, except what? So let's just look at the first piece, for example. Okay, so let's just look at this piece from N1 to this one. So it's kind of a lesson to be learned, right? Okay. So the quotient looks like this thing over here. No? So what happens when I apply the induction to this? So let me just drop these things, okay? So what happens when I apply the induction here? You know what? I have a short exact sequence. I apply this functor induction, what happens? What's the next term after that?
R1.
It's R1, right? Okay. Now, I have a filtration for H0, and I want to show that H0 has a good P filtration. Well, if I take this over this, right, I can't guarantee that it's isomorphic to this. If I could, I would be okay by using this identity up here. Does that make sense? So I need to show that the R1 is 0. Okay. And the way I can show the R1 is 0 is to actually use, so the idea is you need to show that the R1 induction is actually equal to 0. Okay, so once you do that, we're done.
Can you say again why you need that?
Because I want to identify that this over this with the induction from N2 over N1. And once I do that, N2 over N1, it looks something like this. And the induced module looks something like that. Okay. Otherwise, we don't know whether the quotient is actually of this form. Right? That's what we want.
It's kind of like lifting this filtration somehow.
Well, just making sure there are no cancellations. That's the point, right? So when you take a filtration, and you take this like left exact functor, you just want to make sure that, you know, the quotients here behave like you want them to in terms of taking the induction on the quotient. Okay. To guarantee that, you need the R1 to be 0. Okay, does that make sense? There's a common trick that you use. You just can't sort of blindly, you know, apply the induction functor and say, oh, it has a filtration. It does have a filtration, but we don't have any control over the subquotients unless we know something about the R1.
Like in this one, you'd be taking the quotients of inductions, and you want the induction of.
Yes, yeah, that's right. That's exactly it. All right. Now, let's just look at this more closely, okay? And then we'll be done. All right. Okay, so N1 here, we could assume that N1 is some irreducible representation. So R1 induction of N1, in the first case is just R1 induction. Let me put this in. This is GRP to G of what? LR, we're going to call it sigma 0, tensor PR sigma 1. Some irreducible down over here. This is a composition series. Okay, so what we do is we sort of do the same trick. So we use a tensor identity. So we use that. But remember our hypothesis. Our hypothesis is that this plus beta check is always bigger than or equal to 0. Okay. So under that condition, we actually showed this earlier. The R1 is 0. So in particular, I mean, if sigma 1 is dominant, you're okay. But remember, the region that this actually holds is actually this region in here. Whereas the dominant region is a little bit smaller than that. Okay, so we know that Kemp's vanishing there, this is going to vanish in here, but we can extend the region a little bit more under this condition. Okay, so this is what it's R1. Okay, and then you just work your way up. So. And the situation, so you can just the thing is, once you have this vanishing, these are all exact sequences. The number of times the P filtration term occurs is the same number of times, you know, the irreducible occurs back in this series. Okay, so you can match the two up just by comparing this series with this series over here. Okay, they just line themselves up because of this exactness. Okay, questions on this? All right, great. So this is how you actually can go to P filtration. Now, unfortunately, you know, this condition, this condition here doesn't always hold. In fact, I mean, my collaborators and I have been looking at this very closely, and we've actually refined this theorem so we can actually produce P filtrations or PR filtrations with a weaker condition than this.
Can you actually use the method of the theorem to explicitly construct a filtration?
Yeah, that's
for
what
examples.
That's what we did over here.
Yeah, you just do that explicitly.
Yeah, that's right. Exactly. So once you have a composition series, this gives you a P filtration.
Is finding a composition series that satisfies that pretty difficult though, or is it not that bad?
Well, you know that it doesn't matter what composition series you take, right?
Right.
So it's not so much a matter of, picking the right composition series. You have to have some, you just pick a composition series. The problem is that even though your weight here is dominant, the composition series could have non-dominant weights. That's the problem. And when you sort of build these series over here, it turns out that you can get cancellations. Like in our counter examples, there are cancellations involved. So, it's really an interesting problem.
So in practice, if you're trying to find these composition series, you just look for submodules and then check if there are some more fixed or something like that.
Yeah, you can. I mean, there's some combinatorics that you can use at times, but it's very difficult to find composition factors for the series of the disease. That's one of the main obstructions. We can always find a composition series when we knew what the composition factors were. Then we know the characters of the irreducible representations. Good.
Okay, so let me at least state the next theorem. So what we're going to do next is we're going to show strong linkage in the GRT category. Okay, here we go.
So this is linkage.
I think I could call it strong linkage.
So we know we have this strong linkage principle for the H zeros. So you can actually prove it for the GRT category. So it turns out that strong linkage for H0 lambda, this implies the strong linkage for the CRL. Okay, so if I take a composition factor here, it has to be strongly linked to lambda. Okay, so theorem. So let me just state the theorem. I think you'll understand. So let lambda and mu. Okay. So part A is the following. So suppose that I have this, and I have a composition factor here. So suppose this appears inside of here as a composition factor. So then mu has to be strongly linked. Okay. And what else can we say? Oh, well, let's just combine the two. So this is true. Well, if this is true, also then it has to be, these have to be linked under the action of the affine cloud. So mu is in WP. Okay, and actually, I think you have to add a little bit more. Plus PVRX. So it's actually in the action under the affine file group too. Yeah, I'll show you where this works. Okay, how much time do we have? Okay, so let's prove this.
I'll prove this part for sure. Proof. Okay, so if I take ZR prime lambda, this is finite dimensional. Okay. So what I can do is basically I can take this module, I can tensor it by one-dimensional representation, and I can make all the weights, all the composition factors dominant. Okay, so the idea is, let's say this lambda is somewhere down here. Okay, so I can take some big enough dominant weight to throw it into this chamber up here. So so one can tensor by let's see, PR nu, where nu is large, so that CR hat prime and the tensor PR nu as composition factors. LV0, LV1, etc. Let me just say it this way, of the form. LV0 tensor PR1 with all right, so the point is that I take this lambda, it could be like anywhere in this Euclidean space, and then I tensor by something big enough, so I'm way up here. But not just that I have this weight way up here, I can just translate it in sort of the far universes of the dominant region, so that all the composition factors are of this form. They're dominant, and you also have this condition. Okay, does that make sense? All right. Okay, so so now what do we do? Okay, so now okay, so let's see. All right, so I have so I'm going to use this over here, right? And what do I know about the composition factors over here? So that means that if I take mu0, I'll call it mu. So if I take the original composition factors and I tensor by this, this has to be strongly linked to lambda plus PR lambda. Okay. And that's because when I look at A0 lambda, what do we know? Well, we know that one of these guys, let me write it this way. So this thing has a P filtration. Let me write it this way. So lambda plus PR, this has a P filtration. Okay. And the factors look something like this. Compositions factors of this plus PVR nu. And so that means that by strong linkage, this thing has to be linked to this. Okay, so we use strong linkage here. And then, because now what we can do is we can just take off the PVR nus. So that actually does that.
Okay, so the idea is we sort of, not too much time, so the idea is you boost this thing way up to here. You look at the H0 lambda for that, okay? And then all the composition factors of the Z have the right form over here, right? And so you know that this thing has a good P filtration. Yeah. And so when you take this thing, tensor H0 mu1, that's going to be a factor of this. So that means that mu0 plus PVR mu1 has to be strongly linked to this. Okay. And then you just take off the P of the R's. So that's basically it. Okay, any questions on this? All right, so next time what we'll do is we will look at extensions in this category and then look at the Steinberg module. So we'll look at extensions and GRT, and then we'll look at what's called the Steinberg module next time. The Steinberg module is a really important module in representation theory, so I should actually define what it is. And then later on, we'll actually show that the Steinberg module actually has some very nice properties. Okay, so let me stop here. So wish everyone a safe and happy weekend.